having seen line integrals and certain aspects of its evaluation, we come to the next very important vector integration concept called the surface integration. Here we have a surface S and n cap stands for is unit outward surface normal, and you will be given the field F, F1i plus F2j plus F3k. So we are trying to evaluate what is known as the surface integral F dot n cap ds, or sometimes this is also written as integral F dot ds. Ultimately, it is this that we will have to remember for evaluation. And the surface can again be of two types. It can be an open surface or it can be a closed surface. So let us say if S is a closed surface, we write closed surface integration F dot n cap ds. So surface integral problems basically are of two types, the open type and the closed type. Whenever you are dealing with a closed type of integration, then we have the advantage of the Gauss divergence theorem. So when it comes to these types of situations, you may remember the Gauss divergence theorem, about which I will tell you very soon. One will have to remember a few more issues also, that is surface integral 1 ds. Now this arises when F dot n cap reduces to 1. So when this becomes 1 ds, it is nothing but surface area of the given surface. So this is a special situation which may arise while doing long problems, or sometimes the problem itself may be set to evaluate the surface area. However, there are general formulas to calculate the surface area of a surface in terms of double integrals, about which I will teach you very soon. But first, let us see how one has to evaluate a surface integral, because there are too many things to be done before the integration process starts. The first point you must remember is a surface integral generally cannot be evaluated directly. So what one has to do is, from the given surface, first write the surface normal, unit surface normal. N cap has to be evaluated. So once n cap comes, you take the dot product with the field which is given to you. After this has been reduced to a scalar, the next thing is, what is this ds? Because we have to convert a surface integral into a double integral, therefore either we must project on the yz plane or xz plane or the xy plane. So the pre-processing part of this types of problems will take a couple of minutes, after which the integration starts, and that is always a double integral, unless you are lucky enough to get this type of situation. So let me put in detail how one has to go through the process of setting up the double integral from the surface integral. The unit surface normal is generally given by del phi divided by the magnitude of del phi, where del phi is the gradient vector of the surface. And F dot n cap is evaluated. Then comes what are known as projection formulas. These are formulas for ds. As we discussed, there are three types of projections which are possible. If you project on the yz plane, it is dy dz by magnitude n dot I. If you project on the xz plane, it is dx dz by magnitude of n dot j. And in the last case, if you project on the xy plane, it is dx dy by magnitude n dot k. So, once you have decided the plane of projection, then you must be converting the surface integral into a double integral in that particular plane that you have selected, and the rest you'll have to just follow the rules of double integration, about which we had discussed earlier. Now, well, these things need not be emphasized, but one can see the denominators are very critical. Never choose a projection where the denominator becomes 0. So, that is a basic thing that one will have to remember. And if you go to the next stage, so how does it look like? A surface integral f dot n cap ds would become f dot n cap. Suppose you have chosen this projection, then you would write dx dy by magnitude n dot k, etc. The other possibilities are these two. Right. Now, if S is closed, this is the important situation. What do? Use Gauss divergence theorem. What is this Gauss divergence theorem? It says a closed surface integral f dot n cap ds is identically equal to the volume integral of the divergence of f dv. So, we will be mostly focusing on problems where the use of divergence theorem may become important. Of course, once again, if you have to use the divergence theorem, make sure the surface is a closed surface. Closed surface could be a sphere, or it can be a parallelepiped, that is rectangular box, or it can be a closed cylinder, a closed cone, a tetrahedron, and all these things. So, one must be very alert to the situation, because for these types of competitive exams, you cannot expect a full evaluation of a surface integral or a line integral. Questions are mostly set around the theorems, namely the Green's, the Stokes, and the divergence. So, as we take up an exercise now, let us keep our options open and see where we are with respect to the surface. If it's open surface, there is nothing much we can do. If it's closed, immediately react and think of the divergence theorem. So, let's begin the illustrations. Question number 1. What is the value of the surface integral over the parallelepiped bounded by x is equal to 0, y is equal to 0, z is equal to 0, x is equal to 1, y is equal to 2, z is equal to 3, when the field f is equal to 2xyi plus yz square j plus xzk. This is a problem based on closed surface integration. So, therefore, straight away we will go to the Gauss divergence theorem. So, we will write closed surface integral f dot n cap ds is identically equal to volume integral divergence of f dv. Now, divergence of f is nothing but dou f1 by dou x plus dou f2 by dou y plus dou f3 by dou z dv. Now, this will give us dou f1 by dou x is 2y plus dou f2 by dou y is z squared, dou f3 by dou z is x. The advantage of this problem is the box has got planes which are all parallel to the fundamental planes. So therefore these will themselves become the limits of integration. So how do you do this? X is equal to 0 to 1, y is equal to 0 to 2, z is equal to 0 to 3, 2y plus z square plus x. dv can be expanded as dz, dy, dx, because that is how we fix the order of integration. So I will just show you this integration also. With respect to z, we will get 2yz plus z cube by 3 plus xz from 0 to 3 dy dx. So apply the limits in place of z and you will get 0 to 1. When z is 3, you will get 6y. This is 27 by 3, which is 9 plus 3x dy dx. When you integrate this with respect to y, you will get 3y squared plus 9y plus 3xy from 0 to 1 dx. Of course, 0 to 2 will have to be applied for the variable y. So we get 0 to 1, 12 plus 18 plus 3x dx. Now you can guess the answer. This is already 30. So when you integrate 30 with respect to x, you get 30x from 0 to 1 will be 30 plus. This will be 3x square by 2. We will get some 3 by 2. So that would make it, now in fact here this is 6x, because when y is 2 you get 6. So we will get 3x square, that becomes 3. So the answer is 33. So the very first problem we chose is one where the divergence theorem has to be used, and the evaluation of course is very simple. Correct option for this problem is B. Let's see the next question. Question number 2. What is the value of the surface integral f dot n cap ds, where f is equal to 18zi minus 12j plus 3yk, and s is the part of the plane 2x plus 3y plus 6z is equal to 12 in the first octant. We know plane is an open surface, therefore this is to be done by direct evaluation. So first we find out the surface normal, del phi divided by the magnitude of del phi, where this is the surface. So we'll get 2i plus 3j plus 6k by square root of 4 plus 9 plus 36. So this is nothing but 2i plus 3j plus 6k divided by 7. So we find out f dot n cap, which is 1 by 7 times 18z into 2, 36z minus 36 plus 18y. Then we need a projection formula, and if you can observe the unit surface normal, it contains all the three components, therefore we can project it on any plane. We are all very comfortable with xy plane, so let me project on the xy plane. So the projection formula is dx dy by magnitude n dot k. So this would be dx dy by magnitude of n dot k is 6 by 7. So now what is that we need? We need surface integral f dot n cap ds. F dot n cap is here, ds is here. So this 7 would get cancelled, and then this divided by 6 would give us double integral over r 6z minus 6 plus 3y dx dy. So there is a small problem. The problem is, in this projected plane, the variable z should not appear. So what you do is, you eliminate this z using the equation of the plane. So you replace z with 12 minus 2x minus 3y by 6. So z is equal to 12 minus 2x minus 3y divided by 6. So if you simplify by replacing z with this, you will get double integral over r. 6 would get cancelled here, and then you will have 12 minus 2x minus 3y minus 6 plus 3y dx dy. So just simplify this, and you have double integral over r 6 minus 2x dx dy. So as we discussed, a surface integral should be reduced to a double integral by projecting on a suitable plane. Now what is required is to understand what is there on the xy plane. Now you can see, when this plane is projected on the xy plane, z should be reduced to 0. So this r is nothing but 2x plus 3y is equal to 12. But don't forget, we are in the first octant. In the first octant, yes, x is greater than or equal to 0, y is greater than or equal to 0. That means if you take the combined effect of all these things, you will get the region of integration as a triangle. This is x-axis, y-axis, and this line is this. So what are the intercepts? 6, 0, 0, 4. So this becomes a region of integration. So all that you have to do is evaluate this double integral with respect to this region. So let us see how to write the limits. How are the limits now? X varies from 0 to 6. Y varies from 0 to 12 minus 2x by 3. So this integral will appear as 0 to 6, 0 to 12 minus 2x by 3. And what is the function? 6 minus 2x. The order of integration is dy dx. I will leave this evaluation to the student because everything is now ready. Please confirm 24 is the answer with option A appearing in the sheet. So this is a typical surface integral problem which involves direct evaluation, showing all the features right from the building of the surface normal to selecting a projection formula, and then building the region, fixing the limits of integration, and so on. But if the student was a little bit smart, he would not have gone for the dx dy projection. See, f dot n cap contains the variables y and z, so he could have gone for the projection on the yz plane, which would have minimized a little bit of amount of work here. However, it is not that very important in this question. You can do anything, but managing time ultimately becomes important. So let's go to the next question. Question number 3. What is the formula to find the surface area of the surface z is equal to f of xy? If you denote the surface area by s, then this is evaluated by integral 1 ds. And I will give you 3 formulas here. If the surface equation is like this, then the formula is double integral square root of 1 plus zx squared plus zy squared dx dy. If the surface is y is equal to a function of x and z, then the corresponding formula would be surface integral square root of 1 plus yx squared plus yz squared, where these are partial derivatives. And in the last case, when x is a function of y and z, square root of 1 plus xy squared plus xz squared dy dz. So because in this question this surface was given, the correct option would be that. So we can use this very effectively to find out surface integrals. So let us see two problems where we use this information to find out the surface integrals. And I have reserved some of the best questions on surface integrals for the Gauss divergence theorem. So you may not see many problems today, but because of the nature of this exam, we cannot have long evaluation problems. As I told you, the problems may be revolving around the theorem. So let's do the fourth problem, in which we will see how to evaluate the surface integral. So the correct option for this problem is D. Question number 4. What is the surface area of the plane x plus 2y plus 2z is equal to 12 cut off by x is equal to 0, y is equal to 0 and the cylinder x square plus y square is equal to 16. So the problem is to find the surface area of the plane with projection on the xy plane, which is nothing but the quadrant of a circle. So if you look at this, it represents the quadrant of a circle. So from the plane equation, write z is equal to 12 minus x minus 2y by 2. Compute zx, which is minus half, zy, which is minus 2 by 2. Surface area is equal to square root of 1 plus zx squared plus zy squared dx dy. Simplify this and you get double integral 3 by 2 dx dy, which is 3 by 2 times area of quadrant of the circle. 3 by 2 times pi r square by 4. So this is 3 pi by 8 into square of the radius is 16 and you get 6 pi. So 6 pi means option C is the correct option. So this is a problem based on surface integrals, and it's a short type question, but unless the fundamentals are known, you will not be able to conclude within a minute or so. Let's look at another question of the same type. Question number 5. What is the surface area of the plane x plus 2y plus 2z is equal to 12 cut off by x is equal to y is equal to 0, x is equal to y is equal to 1. Almost similar to the last problem. Write z as 12 minus x minus 2y by 2. Find out zx. Find out zy. Surface area is double integral square root of 1 plus zx squared plus zy squared dx dy. As before, this would be double integral 3 by 2 dx dy over r. Now what is this r? It is described by these equations. So it's nothing but a square. And what are the limits? 0 less than or equal to x less than or equal to 1, 0 less than or equal to y less than or equal to 1. So this is 3 by 2 times area of square. 3 by 2 times 1 into 1, 3 by 2, and the correct option is D. So this is how short type questions in surface integrals can be attempted. Of course, we covered one problem on the divergence theorem. However, when we actually focus on the divergence theorem, we will see some more very good questions. Let us now focus specifically on some Green's theorem problems which are well known. Question number 1. What is the value of the closed line integral minus y cube dx plus x cube dy, where C is the circle x square plus y square is equal to 1? Now first we'll convert this into a double integral using Green's theorem, and then you'll realize you require to use polar coordinates to evaluate the double integral. So that is why this problem has been selected. So for the benefit of students, let us remember dou f2 by dou x minus dou f1 by dou y, double integral of this dx dy is identically equal to closed line integral f1 dx plus f2 dy. This will be the statement of the Green's theorem. Now we are given this, we'll convert it into this one. So this is equal to double integral over r dou by dou x of x cube minus dou by dou y of minus y cube. So you can see this is 3 times double integral over r x square plus y squared dx dy. So it is this which we'll have to evaluate. And what is the region of integration? It is the region enclosed by this circle. So the region of integration is a unit circle whose equation is x square plus y square is equal to 1. So if you use polar coordinates, x is equal to r cos theta, y is r sin theta, x square plus y square is r square, Jacobian is r, which means dx dy is r dr d theta. R varies from 0 to the radius of the circle, theta varies from 0 to. So when you insert all this into the problem, this looks like 3 times 0 to 2 pi, 0 to 1. This is r square, and another r comes from here. So that becomes r cube dr d theta. So when you evaluate this, this becomes r power 4 by 4, and you apply limits and you will get 3 by 4, 0 to 2 pi d theta. So integration of d theta is theta, so this becomes 2 pi. So 3 by 4 into 2 pi is nothing but 3 by 2 pi. So this is how this problem is evaluated, and the correct option is A. So Green's theorem with polar conversion is a very hot type of problem which students have to practice. Let's go to the next question. Question number 2. What is the value of the closed line integral xy plus y square dx plus x square dy, where C is a closed curve of the region bounded by y is equal to x and y is equal to x square? First we trace the region. This is a straight line and this is a parabola. Y is equal to x square, y is equal to x, and the intersection points are 0, 0, 1, 1, and that is the region of integration. So the limits of x will be 0 to 1, the limits of y will be x square to x. So using the statement of the Green's theorem, let us convert this. This is double integral over r dou f2 by dou x, that is 2x, minus dou f1 by dou y, it is x plus 2y dx dy. So this is nothing but double integral over r x minus 2y dx dy, and we have already worked out the limits of integration. So this will be 0 to 1, x square to x, x minus 2y. The order of integration is dy dx. I will leave this as an exercise to the student with minus 1 by 20 as the output, which you will find as option D in the sheet. Let's go to the next question. Question number 3. What is the output of the closed line integral 3x plus 4y dx plus 2x minus 3y dy, where c is the circle x square plus y square is equal to 4. So again we use the Green's statement to convert. So this gets converted into double integral over r. Dou f2 by dou x will give us 2 minus dou f1 by dou y will give us 4. So this is minus 2 times double integral 1 dx dy minus 2 times area of the circle, because the curve is a circle. So minus 2 times pi r square, where r is 2. So this becomes minus 8 pi, and the correct option is C. So no challenge in this problem, absolutely. But this will contrast the first example where we had x square plus y square in the function, and therefore polar coordinates became necessary. Here this is straightforward area evaluation. Let's go to the next question. What is the output of the closed line integral 3x square minus 8y square dx plus 4y minus 6xy dy, where C is the boundary of the region defined by the lines x is equal to y is equal to 0 and x plus y is equal to 1. First, let us draw the region of integration. The region, as you can easily see, is a triangle. X is equal to 0 is the y axis, y is equal to 0 is the x axis, and this is a line x plus y is equal to 1, and the region of integration is that triangle in the first quadrant. So you can see x limits vary from 0 to 1, y limits vary from 0 to 1 minus x. So this will be used as limits of the double integration after conversion. The conversion takes place using the Green's theorem. So double integral over r, dou f2 by dou x is 0 minus 6y. So it is minus 6y minus dou f1 by dou y is 0 minus 16y. So this is double integral over r 10y dx dy, and the limits are available. So x is equal to 0 to 1, y is equal to 0 to 1 minus x, 10y. The order of integration is dy dx. So when you evaluate this, this becomes 5y squared from 0 to 1 minus x dx. So let us do this calculation. This becomes 0 to 1, 5 times 1 minus x whole squared, 1 minus x whole squared dx. Need not expand, but you can directly integrate. You will get minus 5 times 1 minus x whole cube by 3 from 0 to 1. So this will be minus 5 by 3. Upper limit makes it 1 minus 1 0, lower limit makes it 1 minus 0 1. So 5 by 3 is the output, and you can see A is the correct option. So with these illustrations we come to the end of examples on Green's theorem. So what remains is the Stokes and the divergence theorem, which we will cover in the next lecture.